Today we are going to talk about the 13C-NMR spectra of inorganic complexes. So this is a very simple topic. So here we mainly talk about the fluxional molecules. Okay, so we'll take one example, that is FeCO5. Okay, so in the FeCO5, so the structure looks like this. Okay, so this is the structure. In the structure we can see two carbonyl groups are there. So equatorial carbonyl group and axial carbonyl group. Okay, so if we record 13C-NMR for FeCO5 complex, so we supposed to get a two peak. So one is for axial, another one is for equatorial. The intense one will be for axial equatorial, and less intense one will be for axial. But this is we are observing at low temperature. And the same spectra, if we record at a high temperature, we are getting a single peak. So at high temperature we are unable to see the axial and equatorial, but whereas at low temperature we can able to see axial and equatorial. The reason here is, and if we go the numbering for carbonyl groups, so this should be 1 2 3 4, and sorry, this is 5 and this is 4. Okay, so what's happening here, there is a exchange between 2 and 5 as well as 3 and 4. So at high temperature the exchange between the axial and equatorial is taking place between 2 and 5 and 3 and 4. So this, because of this reason at high temperature we are getting a single peak, whereas at low temperature this exchange will be it will not be that dominant. If we want to get NMR, if we want to differentiate axial and equatorial, the rate of exchange should be equals to NMR time scale. Okay, so at high temperature the rate of exchange is very fast compared to the NMR time scale. Because of that reason, so NMR could not able to identify axial and equatorial. Because of that we are getting a single peak, whereas at low temperature rate of exchange is almost equals to the NMR time scale. So because of that reason we are getting a two peak. So at this low temperature NMR can identify axial as well as equatorial. So because of that reason we are getting a two peak for FeCO5 at low temperature. And next example we have here Fe2CO9. so the structure looks like this. So as we can see in this structure, so there are two different types of carbonyl groups we have. So this is terminal and this is bridging. So two different carbonyl groups we have. One is terminal, another one is bridging. So if we record 13C for this complex at high temperature, we get only single peak. So even though we have two different carbonyl groups here, but at high temperature we will get only single peak. Here also the reason is there is exchange between the bridging and axial, bridging and terminal. Sometimes terminal is becoming bridging and bridging is becoming terminal. So for the same complex, if we take at low temperature, we will get a two peak. The intensity is very important here at low temperature. So intensity wise, terminals are 6 and bridging are 3. So it will be, here we have CO bridging and CO terminal. So terminals are 6 and bridging are 3. So we have a peak intensity in the 1:2 ratio. So this is one is for the bridging, CO bridging, and this one will be the CO terminal. So this is about the Fe2CO9. And another important example we have now, that is CO2 CO8. Okay, so this exists in two forms. In the liquid state it exists in different form. Then in the solid state so this is in the liquid state and this is in the solid state. So in the liquid state all carbonyl groups are terminal carbonyl groups, whereas in solid state two carbonyl groups are bridge and remaining are terminal carbonyl groups. So here if they ask in examination point of view which technique is better to identify CO2 COA structure in the liquid state and solid state, IR spectroscopy is good because we can identify just like that, because this will shows around 2143 centimeter inverse and this shows around 2053 something like that. So IR is the best technique to identify the structure of CO2 CO8 in the liquid state and solid state, but we can identify this one by using a 13C-NMR also, because for here we will get only singlet we will get only one peak even at high temperature as well as low temperature, but whereas in this case we may get two different peaks at low temperature. So 13C also can useful for identifying this complex, but IR is a better technique to identify these complex structures at liquid state as well as solid state. And next example we have Fe3CO12. So the structure looks like this. One, two, three, 4, 5, 6, 7, 8, 9, 10. 10, 11. So this is the structure for Fe3CO12. So as we can see here at room temperature same thing, we will get a single peak because there will be an exchange between the axial as well as bridging as well as terminal. But at low temperature we will get a two peak with 1:5 ratio. Okay, so the 1 is for CO bridge and 5 is for CO terminal, because there how many terminals are present here? 10 carbonyl terminals are present and 2 carbonyl bridgings are present. So 10 carbonyl terminals and 2 carbonyls are bridge, so this will be a 5:1 ratio. So the intensity wise bridging one will be more intense, terminal one will be more intense compared to bridging one. So this is about the Fe3CO12. And next we have C6H6 CrCO3. So this structure looks like this: CO, and here benzene. Okay, so first we have to see whether it is a N6 or something else. So if we calculate an for this complex, it should be an6. That means chromium is attached to all the carbons. That means all carbons are equivalent here. Okay, and another thing, this carbon is also equivalent. So here we have two different carbons, so we'll get a two peaks. And as we see this benzene, normally this in 13C benzene peaks comes around 120 to 150, but since here it's attached to the metal, that this chemical shift value will goes upfield shift compared to normal benzene, because there will be some back bonding between the metal to the benzene pi electrons. Because of that reason chemical shift value will shifted to the upfield region in this case. And not only this one, anything like we can take in this salt also. So normally where this olefin peak come around 4.5, but after forming bond with platinum, there is some back bonding from the platinum to pi electrons of the ethylene. So because of that reason electron density on the ethylene is increasing. So because of that, upfield shift will takes place. And next we have vanadium CO5 Br. CO. So here also we have two different types of carbonyl compounds. So we can see that one carbonyl group which is trans to the bromine, so another carbonyl groups which are cis to the bromine. Okay, so we know that here only this. So in the octahedral complex, we know that 3 trans positions are there and 12 cis positions are there. So only these 3 are trans positions. Okay, if you are talking with respect to this, so this is the this will be the trans to this. Let's say this is A, this is B, C, D, E, F. So here A with respect to A, B is in the trans. Remaining C, D, E, F, everything is in the cis only. Okay, so like that we will get 12 cis forms and 3 trans forms. So now here one carbonyl group which is a trans to the bromine, and another carbonyl or remaining carbonyl groups, they are cis to the bromine. So we have a 4 CO is to 1 CO. So the ratio will be like that. So we'll get a 2 peak. And another thing, how the chemical shift value affects from going from the 3D to 5D. So we have 3 complexes here: chromium CO6, molybdenum CO6, and tungsten CO6. So as we go from the top to down, the back bonding will be increased. So because of that reason, on the metal the electron density will increases. If electron density will increases, means like so as we go from the 3D to 5D, back bonding is increasing. So back bonding increasing means electron density on the carbonyl group is increasing. So automatically what will happens, the chemical shift of the CO will decreases. So this comes under around 221.3. This one I think around 199 something, and this is I am sure that 191.4. So as we go from 3 to 45D, the chemical shift value is decreasing because of the back bonding is increasing in these cases. So because of that chemical shift value is decreasing. So this is about the 13C-NMR for inorganic complexes, and next I will make video on photon 19F on 31P. Thank you.